In July 2025, astronomers confirmed 3I Atlas, the third interstellar object to visit our solar system, bigger and faster than Oumuamua and Borisov, racing at 58 kilometers per second. For the first time, NASA's new SPHERex telescope captured early observations of the comet alongside Hubble and JWST, revealing its structure, size, and chemistry. This rare cosmic visitor is offering fresh clues about how comets form and what they can teach us about distant planetary systems. When 3E Atlas was first detected in early July 2025, astronomers quickly realized it was unusual. Its orbital calculation showed an eccentricity of about 6.2, too far beyond what the Sun's gravity could hold, proving that it originated outside our solar system. Its velocity of 58 kilometers per second made it the fastest interstellar object yet observed. Early telescope images showed a diffuse glowing body, hinting at a surrounding coma. Initial estimates of its nucleus suggested something very large, possibly 10 to 30 kilometers across. But these values were uncertain since the bright coma made it difficult to separate the solid core from the surrounding dust and gas. A clearer picture came on July 21, 2025, when the Hubble Space Telescope observed the comet. Hubble revealed the nucleus was much smaller than first thought, likely no larger than 5 kilometers across. The brightness was dominated by its expansive coma, while no tail was visible, a surprising contrast with many comets that develop long tails when heated by sunlight. Then in early August, two other space observatories added crucial details. SPHERex, operating between August 7 and 15, recorded the comet in infrared. It detected a bright extended halo of carbon dioxide, CO, gas and dust streaming away from the nucleus. Notably, SPHERex did not detect significant water vapor or carbon monoxide, two volatiles that usually appear in comets. JWST, observing on August 6, confirmed the strong CO signal and added nuance. It picked up faint evidence of water ice, a small amount of water vapor, and traces of carbon monoxide, offering a more complete chemical fingerprint. Hubble sized the nucleus, SPHERex detected CO outgassing, and JWST found water ice, together giving 3E Atlas a full profile within weeks. This teamwork proved the power of combining telescopes to study rare, fast interstellar visitors. Why does studying 3E Atlas matter? Interstellar comets are fragments of other planetary systems. Unlike meteors or dust that might drift between stars, objects of this size are intact remnants from worlds forming around distant suns. Each one that enters our solar system carries chemical clues about how other star systems evolve. The first interstellar visitor, Oumuamua, was puzzling, small, elongated, and lacking typical comet activity. Its behavior was so unusual that some even speculated about artificial origins. The second, Borisov, looked much more like a conventional comet, rich in volatiles such as carbon monoxide. It seemed like a freshly ejected body from a Kuiper belt-like region around another star. 3E Atlas appears to fall between these two cases. Its activity is dominated by CO, with only faint signs of water and carbon monoxide. This resembles Comet Hartley 2 in our own solar system, an older comet that produces bursts of CO while showing limited water activity. The similarity suggests that Atlas is an evolved comet, not pristine like Borisov, but not depleted like Oumuamua. It likely came from the Milky Way's thick disk, losing fragile ices over billions of years, leaving CO and water as its main activity drivers. The water detection, though weak, is significant. It hints that water ice still exists within the nucleus but remains insulated, only releasing vapor once the comet is heated enough as it nears the Sun. Stronger water activity could emerge, providing a test of this theory. Together, Oumuamua, Borisov, and Atlas suggest a progression, Oumuamua as an exhausted remnant, Borisov as a volatile-rich fresh object, and Atlas as an intermediate stage. This sequence helps astronomers outline how interstellar comets age and evolve depending on their composition and journeys through space. The story of 3E Atlas is still unfolding. The comet is heading toward perihelion, its closest approach to the Sun, expected at the end of October 2025, at about 1.36 astronomical units, a distance slightly inside Mars' orbit. During perihelion itself, Earth will be on the far side of the Sun, making direct observation difficult. But the months before and after will provide opportunities. As the comet warms, astronomers will be watching for changes in its activity. If deeper layers of water ice begin sublimating, we could see stronger water vapor signatures or even faint tail features not yet observed. If CO continues to dominate, it would confirm that Atlas is largely depleted of lighter ices, reinforcing the view that it is an evolved object. Beyond telescopes, scientists have considered whether existing spacecraft might observe it. While no mission was designed to intercept Atlas, instruments aboard Mars orbiters or other planetary probes could attempt opportunistic studies. Though such efforts would be technically challenging, even limited spacecraft data could provide a valuable perspective. Looking further ahead, the real breakthrough will come from the Vera-Cu Rubin Observatory. With its wide-field survey capabilities, Rubin is expected to detect many more interstellar objects, potentially dozens each decade. That means 3E Atlas is not a once-in-a-generation event, but the beginning of a new era where interstellar visitors can be studied routinely. The broader implication is profound. Interstellar comets are essentially natural messengers. They carry the chemical fingerprints of other planetary systems, offering us direct samples without the need to send spacecraft across light years. Each one adds to the comparative picture of how solar systems form, what materials they produce, and how these bodies evolve. 3E Atlas, once a faint dot, is now a well-studied interstellar comet, bridging Oumuamua and Borisov, powered by a Comet, and revealing the building blocks of other worlds. It marks a turning point in how we study cosmic visitors. Stay tuned. Each interstellar messenger brings us closer to understanding the galaxy beyond the Sun.